Welcome to the Complete Navigator, Mastering the Elements. Throughout human history, the open ocean has represented both the ultimate boundary and the ultimate frontier. To traverse thousands of miles of featureless blue without a single landmark required far more than physical bravery. It demanded an extraordinary synthesis of science, mathematics, environmental intuition, and engineering mastery. In this comprehensive exploration, we will trace the grand arc of navigation, a discipline born from observing the steady rotation of distant stars and perfected through centuries of marlinspike seamanship, hydrodynamics, and aerodynamic principles. We will examine how ancient civilizations first translated celestial geometry into survival, how medieval scholars codified the heavens into paper engines of exploration, and how modern mariners harness vector physics and fluid dynamics to carve a precise course across the sea. Whether examining a 3,000-year-old Babylonian clay tablet or adjusting a modern yacht's mainsheet under a stiff breeze, the core objective remains unchanged: to understand the invisible forces of nature and bend them to human intent. Join us as we navigate from ancient almanacs to the art and science of sailing.
Long before mariners possessed magnetic compasses or mechanical clocks, the night sky served as humanity's primary orientation matrix. Navigation did not begin on the water. It began on land as a vital survival mechanism tied to seasonal agriculture and environmental forecasting. Around 2000 BC, in ancient Babylonia, priests and astronomers began systematically logging planetary movements on cuneiform clay tablets. By tracking the cyclical positions of Venus, Jupiter, and Mars, they constructed early predictive models for weather patterns and seasonal shifts. In ancient Egypt, celestial observation took on divine and economic significance. The heliacal rising of Sirius, the brightest star in the night sky, served as an infallible harbinger of the annual flooding of the Nile River, providing the precise timing needed to sustain Egyptian agriculture. Meanwhile, in classical Greece, astronomers engineered the parapegma, an ingenious interactive stone calendar fitted with movable wooden pegs. By advancing these pegs day by day alongside carved astronomical inscriptions, the Greeks mapped stellar risings against expected wind patterns, weather changes, and nautical conditions. These early tools proved that the cosmos operated under predictable mathematical laws, a fundamental realization that laid the groundwork for oceanic navigation.
As trade routes expanded beyond sight of land, observational memory was no longer sufficient. Navigation required standardized, portable, and mathematically rigorous reference materials. The transition from oral tradition to codified science accelerated dramatically during the late Middle Ages and the Renaissance. In 1267, the English Franciscan friar and polymath Roger Bacon formally introduced the term almanac in his monumental work, Opus Majus. Derived from Arabic roots, the word represented tables calculating the future positions of celestial bodies. Bacon recognized that if a navigator knew where a star ought to be at a given hour, its observed altitude could unlock their latitude on Earth. 2 centuries later, in 1474, the German astronomer Johannes Muller, better known as Regiomontanus, published his revolutionary Ephemerides. Utilizing Johannes Gutenberg's recently invented movable type printing press, Regiomontanus mass-produced precise astronomical tables spanning decades into the future. These printed ephemerides became the indispensable data engines that fueled the Age of Discovery. Armed with Regiomontanus's tables, explorers like Christopher Columbus, Vasco da Gama, and Ferdinand Magellan could venture into uncharted oceanic voids, confident that the printed page held a permanent mirror to the sky.
While calculating latitude, one's north-south position, was relatively straightforward using the height of the North Star or the noon sun, determining longitude, one's east-west position, remained the deadliest mathematical conundrum in maritime history. Because the Earth rotates 360 degrees every 24 hours, 15 degrees of longitude directly correspond to 1 hour of time difference. To know your exact longitude at sea, you needed to know the exact local time at a reference meridian simultaneously with your local solar time.
For centuries, shipwrecks caused by navigational error claimed thousands of lives and vast fortunes. The crisis reached its zenith in 1767 when the Astronomer Royal, Neville Maskelyne, authored the first official edition of the Nautical Almanac and Astronomical Ephemeris at the Royal Observatory in Greenwich, London. Maskelyne's work provided pre-calculated lunar distance tables, allowing mariners to use the moon as a celestial clock face. When combined with John Harrison's concurrent breakthrough in mechanical marine chronometers, clocks that maintained absolute precision amidst the motion and tempests of the sea, the longitude problem was finally solved. For the first time in human history, navigators could determine their exact position in the middle of a featureless ocean with pinpoint mathematical accuracy. The concept of the almanac soon transcended deep-sea navigation, becoming the definitive repository of practical knowledge for civilian life, commerce, and global seamanship. In 1732, Benjamin Franklin published Poor Richard's Almanac under the pseudonym Richard Saunders. Blending astronomical calculations, weather forecasts, and pragmatic philosophy, Franklin demonstrated the immense public value of accessible tabular data. Decades later, in 1792, Robert B. Thomas launched the Old Farmer's Almanac, which remains the oldest continuously published periodical in North America, renowned for its secret weather prediction formula based on solar activity. By the 20th century, publication evolved into the World Almanac and Book of Facts, transforming into an encyclopedia database for global industry, aviation, and diplomacy. Yet at sea, the traditional almanac never lost its vital function. Today, under the International Maritime Organization's SOLAS Convention, the Safety of Life at Sea mandate, every commercial and ocean-going vessel is legally required to carry official, updated nautical almanacs and navigational charts. Even in an era dominated by satellite navigation and digital displays, the physical printed almanac remains the ultimate, tamper-proof safeguard against electronic failure. Having established where we are on the globe through the celestial geometry of almanacs and coordinates, we now cross a vital threshold in the navigator's craft, translating theoretical position into physical motion. In the Italian sailing tradition, instructors often pose a fundamental question to aspiring mariners. Voi fare vela? Literally translated, do you want to make sail? It is a phrase that carries deep philosophical weight. Making sail is not merely a passive act of drifting with the breeze. It is an active, dynamic discipline of engaging with environmental mechanics. To command a sailing vessel requires a profound shift in mindset. The mariner must learn to read invisible fluid forces, converting atmospheric pressure differentials into controlled forward propulsion. The celestial grid tells us where we must go. The physics of the rig and hull dictate how we get there. We now transition from the macrocosm of heavenly orbits to the microcosm of hull dynamics, wind angles, and marlinspike seamanship. To navigate the boundless surface of the Earth, cartographers created a standardized geometric coordinate system superimposed over the planet's curvature. This grid rests upon two primary axes, parallels of latitude and meridians of longitude. Latitude lines run horizontally, parallel to the equator at 0 degrees, measuring distance north or south toward the poles. Longitude lines run vertically, converging at the geographic poles, anchored by the prime meridian at Greenwich, London. At sea, standard imperial or metric miles are discarded in favor of the nautical mile. A nautical mile is not an arbitrary length. It is derived directly from the geometry of the Earth itself, defined mathematically as exactly 1 minute of arc along any line of latitude. Because 1 degree contains 60 minutes, 1 degree of latitude equals 60 nautical miles, establishing a universal bridge between chart measurement and physical distance. In modern international standards, 1 nautical mile is fixed at precisely 1.852 kilometers. Speed at sea is measured in knots. Historically measured by casting a wooden log attached to a knotted line over the stern and counting the knots running through a sailor's hands during an hourglass interval, 1 knot represents a velocity of exactly 1 nautical mile per hour. On land, directions like left and right are relative to the direction an individual happens to be facing. At sea, where immediate clarity can mean the difference between survival and catastrophe, relative terms are dangerously ambiguous. A vessel requires an absolute frame of reference, internal to its own geometry. The left side of a vessel, when facing forward toward the bow, is designated as port, traditionally lit at night by a standard red navigation light. The right side is designated as starboard, marked by a green navigation light. The origins of these terms are deeply rooted in maritime history. Starboard derives from the Old Norse stjornborði, meaning steering side, referring to the side-mounted steering oar used before stern-mounted rudders were invented. Because sailors steered from the right, ships traditionally docked on their left side to protect the delicate steering paddle, giving rise to port. This absolute nomenclature is linked metaphorically to ancient Mediterranean sailing lore. The western horizon, where the sun sets, was known as ponent, associated with port, while the eastern horizon of sunrise was levant, associated with starboard. To the experienced navigator, wind is not merely moving air. It possesses a distinct personality, temperature, humidity, and atmospheric signature depending on its origin. Nowhere is this more apparent than in the Mediterranean basin, the historic cradle of Western seamanship. Classical Mediterranean mariners identified 8 primary winds, arranging them around the wind rose, the direct precursor to the modern compass card. 1. Tramontane, north, a cold, dry, fierce wind driving down from the Alps. 2. Greco, northeast, a strong, icy blast originating over Greece and the Eurasian steppes. 3. Levant, east, a humid, cloud-bearing wind originating in the eastern Mediterranean sunrise. 4. Sirocco, southeast, a scorching, dust-laden gale blowing directly from the Sahara Desert. 5. Austro, south, a warm, gentle southern breeze. 6. Libeccio, southwest, an unstable, squally wind crossing over Libya and the Central Sea. 7. Ponent, west, a steady, temperate western breeze bringing moist Atlantic air. 8. Mistral, northwest, a powerful, violent, katabatic gale sweeping down the Rhone Valley. Mastering navigation required intimate familiarity with each wind's unique behavior, allowing captains to anticipate storms hours before they struck. Just as the navigator must read the air, they must continuously evaluate the state of the water. In 1805, Rear Admiral Sir Francis Beaufort of the British Royal Navy standardized visual sea observations into a empirical 13-point rating system known as the Beaufort Wind Force Scale. The Beaufort scale categorizes sea conditions based on wave height, foam density, spray, and surface texture. Force 0, flat. The sea surface is smooth as a glass mirror, reflecting light without distortion. Force 133, calm to gentle breeze. Small ripples transform into short wavelets with glass-like crests that do not break. Force 4 through 6, moderate to strong breeze. Moderate waves form longer shapes. Whitecaps become prominent, producing rhythmic ocean whitehorses and airborne spray. Force 7 through 9, high wind to strong gale. Sea heaps up into large breaking waves. Foam is blown in dense white streaks along the direction of the wind. Force 10 through 12, storm to hurricane. A terrifying, chaotic maelstrom. Towering, overhang waves smash with immense kinetic force. The air is filled with driven foam and blind spray, severely degrading visibility. Recognizing these sea states enables a captain to reef sails early, secure heavy gear, and preserve structural hull integrity. Perhaps the most extraordinary achievement of sailing science is the ability to travel upwind, climbing against the very force pushing against the vessel. A sailboat cannot sail directly into the wind. Doing so places the vessel in the head-to-wind position, also known as the no-sail zone, typically an arc of 45 degrees on either side of the wind source, where sails luff uselessly like flags. However, by angling the sails relative to the wind vector, a vessel utilizes complex aerodynamic principles. Close hauled, about 45 degrees, sailing as tight to the wind as possible.
The sail acts as a vertical airplane wing, generating aerodynamic lift rather than simple push force. Low pressure on the leeward side of the sail pulls the boat forward and sideways. Close reach, a slightly freer, faster angle with reduced boat heel. Beam reach, 90 degrees. The wind blows directly across the side, beam of the boat. This is mathematically the most stable, efficient, and fastest point of sail for most hull designs. Broad reach, about 135 degrees, sailing with the wind coming over the rear quarter. Running, 180 degrees, sailing dead downwind. Here, lift disappears entirely, and propulsion relies purely on aerodynamic drag, pushing the boat forward.
To reach an upwind destination, a sailboat must execute a series of sharp zigzag tracks known as beating. This requires executing two fundamental maneuvers. Tacking involves turning the bow of the vessel through the no-sail zone into the wind. As the wind crosses from one side of the bow to the other, the crew sheets in the sails tightly, changing direction while maintaining positive headway. Jibing, or gibing, is the downwind equivalent, turning the stern of the vessel through the wind vector. Because the boom swings rapidly across the cockpit from one side to the other under full wind force, jibing requires careful control to prevent structural damage or crew injury. When multiple vessels operate in the same waters, collision avoidance relies on strict international regulations for preventing collisions at sea, COLREGs. 1. Starboard tack over port tack. A vessel with the wind coming over its starboard side has the right of way over a vessel on port tack. 2. Leeward over windward. When two vessels are on the same tack, the vessel furthest downwind, leeward, having less maneuvering flexibility, holds the right of way over the upwind, windward vessel. The engine of a sailing vessel rests upon a highly engineered compression-tension framework known as the rig. At the center of this architecture is the mast, a massive vertical spar engineered to withstand severe downward compression and lateral bending forces. Because a tall, slender mast would buckle under immense wind loading, engineers incorporate horizontal struts called spreaders. Spreaders push standing rigging wire outward from the mast profile, widening the angle of tension and creating structural triangles that transfer rig loads down into the hull chain plates. Extending horizontally from the base of the mast is the boom, a heavy control spar that manages the foot of the primary mainsail. The entire assembly is secured by two classes of rigging. Standing rigging, fixed high-strength stainless steel wires or carbon fiber stays, forestay, backstay, shrouds that permanently support the mast structure. Running rigging, dynamic ropes, halyards to hoist sails, sheets to control sail angles that enable real-time tactical adjustments by the crew. Together, this framework forms an unbreakable vertical spine, capable of absorbing megajoules of atmospheric energy. If the mast is the spine of the vessel, the sails are its flexible engines. Modern sails are crafted from high-modulus synthetic fibers like Dacron, Kevlar, or molded carbon laminates, designed to hold perfect aerodynamic foil shapes without stretching under load. A standard modern rig utilizes two primary working sails. Mainsail, set aft of the mast, attached along the boom. It provides primary balance, steering drive, and lateral trim control. Jib or genoa, set forward of the mast along the forestay. The overlap between the jib and mainsail creates a high-velocity air channel called the slot effect, accelerating air over the mainsail's leeward surface to dramatically increase overall aerodynamic lift. Every triangular sail shares three primary corners. Head, the top corner hoisted up the mast. Tack, the lower forward corner secured to the deck or boom base. Clew, the lower aft corner attached to control sheets for trimming angle. For downwind sailing, specialized lightweight symmetrical or asymmetrical sails like spinnakers and parasailers are deployed, billowing out like massive parachutes to capture maximum drag propulsion. While the sails capture energy in the air above, an equally critical dynamic occurs beneath the surface of the water. Air pressure on the sail grid does not merely push a boat forward, it creates a massive side thrust force, attempting to blow the vessel sideways and capsize it. Forward momentum is made possible through a delicate hydrodynamic equilibrium between two invisible physical forces. First, center of effort, CE. the theoretical geometric point on the sail plan where the total aerodynamic force of the wind is concentrated. Second, center of lateral resistance, CLR, the focal point of hydrodynamic resistance generated by the underwater profile of the hull, rudder, and most importantly, the keel. The keel is a heavy foil-shaped fin projecting deep into the water beneath the hull, often ballasted at its bottom with a dense lead or tungsten bulb. As wind pushes the sails to leeward, the keel generates counter-hydrodynamic lift in the water, preventing leeway, sideways drift. Simultaneously, as the ship heels over, the ballasted keel creates a massive counteracting righting moment, leveraging gravity to keep the ship upright and converting tipping force into pure forward motion. In an environment governed by extreme dynamic loads, mechanical fasteners like screws or clamps are often impractical. The ultimate reliable bond at sea remains marlin spike seamanship, the art of tying specialized nautical knots. A true sea knot must fulfill 3 uncompromising criteria. It must hold securely under immense tension, resist slipping in wet conditions, and remain easy to untie after the load is released. 6 fundamental knots form the cornerstone of seamanship. 1. Bowline. Known as the king of knots, it forms a temporary, non-slip loop at the end of a line, perfect for securing halyards or mooring lines. 2. Clove hitch. A quick, effective knot used to secure temporary lines or fenders to posts and railings. 3. Reef knot, square knot. Designed for tying together 2 lines of equal diameter or securing reefed sail fabric. 4. Figure 8. The definitive stopper knot, preventing line ends from accidentally running through blocks or deck sheaves. 5. Cleat hitch. The mandatory method for securing halyards and sheets to deck cleats safely under high load. 6. Cow hitch. A simple, strong loop attachment for securing ring fittings. Mastery of these fasteners is a core prerequisite for vessel safety and crew coordination. When a vessel leaves the harbor, it enters an environment of physical isolation. Survival depends on standardized, universally recognized methods of communication across visual and radio spectrums. Visual communication utilizes the International Code of Signals, a system of colored flags where each flag represents a specific letter and an immediate nautical message. For example, the Alpha flag signifies a diver down. Bravo indicates dangerous cargo. In low visibility or night operations, light signals communicate via Morse code. For voice communication over VHF marine radio, strict protocols govern safety communications, categorized into a 3-tiered auditory hierarchy. 1. VHF Tier 1, Mayday, repeated 3 times, the absolute highest priority call, reserved strictly for grave, imminent danger to human life or the immediate loss of the vessel, requiring immediate emergency intervention. 2. VHF Tier 2, Pan-Pan, repeated 3 times, signifies an urgent situation concerning the safety of a vessel or person, such as engine failure in open water or a medical issue, that does not pose immediate threat to life. 3. VHF Tier 3, Security, repeated 3 times, broadcasts vital safety warnings, such as approaching severe gale warnings, drifting hazards, or malfunctioning navigational lights. While celestial navigation guides ships across deep oceans, nearing land requires the high-precision art of coastal piloting. Even in the modern era of satellite GPS, which can be jammed, spoofed, or lose power, truly competent navigators regularly verify their position using optical geometry. This process begins with taking compass bearings on visible, known terrestrial landmarks, such as lighthouses, prominent mountain peaks, headlands, or island edges, using a hand-bearing compass or marine sextant. Each observed bearing provides a line of position, LOP, a straight line drawn on the nautical chart passing through the observed landmark upon which the vessel must lie. A single LOP tells you are on that line, but not where along it. By taking 2 or more bearings on different landmarks in rapid succession, the lines intersect on the chart grid. The point where these lines of position cross is known as the fix. Obtaining a clear 3-point intersecting fix provides undeniable physical proof of the vessel's location, completely independent of electronics. We have journeyed across centuries of human ingenuity, from the cuneiform tablets of ancient Babylonia and the printed ephemerides of the Renaissance, to the aerodynamic foils, hydrodynamic keels, and vector geometry of modern sailing vessels. What then defines the complete navigator? It is not merely the possession of modern tools, nor is it purely an intellectual understanding of charts and physics. The complete navigator is one who achieves a seamless synthesis between the macrocosm of the universe and the microcosm of their ship. They look up at the night sky and see not just distant lights, but an absolute geometric clock and compass. They look down at the ocean and read the rising sea states, atmospheric wind shifts, and subtle underwater forces acting upon their hull. The complete navigator respects the heritage of seamanship while commanding modern technology with quiet, decisive competence. They possess the knowledge to plan the voyage, the physical skill to handle the vessel through tempest or calm, and the humility to honor the untamed power of the sea.
Fair winds and following seas. May your wind always blow from a favorable angle. May the waves gently push your stern forward toward your destination, and may your knowledge of the sky and sea bring you safely home to port. Thank you for joining us on this exploration of the complete navigator. May your charts be accurate, your knots hold fast, and your voyages be filled with discovery. Fair winds, following seas, and clear horizons to you all.